everyone, my name is Ana Sainz, PhD student in the University of La Rioja, Spain. In this video, we will talk about plasma-activated water. We will start with some theoretical issues, then we will explain different methods to measure plasma-activated characteristics, and finally we will talk about how we can modify some plasma-activated water parameters. So, plasma-activated water is generated by treating water with cold atmospheric plasma. In this video, we will focus on different purposes: biological decontamination and chemical decomposition. Let's start talking about some characteristics of plasma-activated water. It's known to have low pH, high conductivity, and high oxygen reduction potential due to the presence of reactive species. It's also known the higher the treatment time, the higher the values of those parameters and the lower the pH. Here we can see how some reactive species interact with other ones in the gas phase, gas-liquid interface, and also in the liquid phase. We can see also these reactive species because they are the most important ones. But how are those reactive species generated? So here we can see the main pathways to create and destroy those reactive species. For example, ozone comes from gas phase and is diffused into water. Then there are three vias for peroxynitrites. This first one is the most known among the researchers. However, peroxynitrite could be also generated by the reaction of these radicals. One of the most important reactive species is hydrogen peroxide, and it's generated when hydrogen peroxide gas dissolved into water, or when OH gas reacts with other OH gas and in contact with water. Other strong radical is OH radical. It comes from the reaction of ozone with water or ozone with hydrogen peroxide, or even when OH gas is diffused in water, forming OH liquid. Finally, singlet oxygen is created when an electron reacts with O2. Even though we have seen how these RONS are generated, is there something more? Yes, photochemical processes. In this slide, we can see how plasma photochemistry influences the generation of different strong reactive species, such as OH radical, NO radical, NO2 radical, or peroxynitrites. Furthermore, there are some plasma-activated waters with strong activity after long times of storage. But why? We know that the lifetime of the most important reactive species is really short. Then, what is happening? At that point, we move to explain the extended biological and chemical effect of plasma-activated water. Now, the answer for this effect is cyclic reactions. For instance, acidified nitrites are really important. It's known that when the pH is lower than 3.5, nitrites are not stable, so they form this acid. This acid also forms NO radical and NO2 radical. Moreover, peroxynitrite is created by all of these pathways. And finally, singlet oxygen is a result of the combination of peroxynitrite with other species. So, we are able to find these reactive species in plasma-activated water after some days or even months due to the cyclic reactions. Once we know the characteristics of plasma-activated water, we should investigate how they can be measured. Here we have different parameters. The first one are pH, nitrites, nitrates, hydrogen peroxide, and ozone. And one of the easier methods is test strips. However, they are not really precise, So if you need more than an approximation, this is not a good method. Otherwise, test strips are not expensive, are portable, and are easy to use. For the same parameters, there are other techniques, such as selective electrodes. Moreover, for those reactive species, chromatography is really useful. Then, for this reactive species, electrospin resonance is used. And finally, spectroscopy is performed in order to measure these reactive species. Now, I would like to explain some of these methodologies. The first one is chromatography. In this case, phenol is used as the product that reacts with each species. Then, the phenol primary degradation byproducts are identified as we can see in this figure. This one is the product after the phenol plus OH radical reaction. This second one after the reaction of phenol plus NO radical. And finally, the byproduct of the reaction of phenol with NO2 radical. Talking about spectroscopy, these are the most common colorimetric assays. PSSI is used in order to measure NO2, and the final product is pink. It is also used in order to measure NO3. However, in this case, NO3 are transformed into NO2. Then the result is the value of the sum of NO2 plus NO3. The second one is titanium reagent. It is used to measure hydrogen peroxide. Then, when hydrogen peroxide reacts with titanium reagent, the final product is yellow. Finally, for ozone, the indigo blue assay is the one used. Despite the advantages of this method, such as the simplicity or the cost, not every reactive species could be measured. For that reason, we will talk about UV-vis spectroscopy. In this case, this is the spectra of a sample of plasma-activated water. This part represents the well-known fingers. There are an overlapping of NO2 and HNO2, which is related with the presence of acidified nitrates, as we explained before. Moreover, at this wavelength, there is another overlapping, this time NO3 plus peroxynitrates. At this point, we could differentiate the absorbance for NO3 and the one for peroxynitrates by following the next steps. First of all, we have to create a calibration line of NO3. Then, we should be able to know the value of NO3 in the sample by other methods, such as selective electrodes. The next step is UV-vis analysis of the sample at the correct wavelength. And finally, the absorbance of the plasma-activated water minus the one of the NO3 is the absorbance of peroxynitrates. It is important to say that after this method, we could compare the absorbance of the peroxynitrates of more than one sample, but we cannot obtain the numerical values of peroxynitrates. We've just explained the theory, so now it's time for practice. We already know that each plasma-activated water is different. Then, if we have two different purposes, which is the best plasma-activated water for each one? After looking bibliography, we know the reactive species which have the strongest bactericidal activity and chemical activity. Then, if we could generate plasma-activated water with more or less species, depending on the purpose, it will be perfect. But is it possible to modify reactive species changing parameters during the generation? In the next slides, we will change the generation time and the gas flow, and we will see how species are different after chromatography and spectroscopy. Let's start with chromatography. Here we have 4 plasma-activated water generation times, and the absorbance of the reactive species increases when the time is higher. However, when the gas flow is higher, those reactive species go down. Furthermore, after spectroscopy, it is observed that every peak is higher when increasing the generation time. It's not in accordance with the gas flow because the fingers are decreased, which is in line of the acidified nitrites in chromatography, as the previous slide shows. To sum up, I would like to emphasize that the configuration to generate the best plasma-activated water is unknown. However, after our investigations, we could suggest the higher activity of peroxynitrites for bacterial activation than the activity of these 3 radicals. We also found that OH radical plays a crucial role when decomposing this chemical molecule. Finally, we saw an increase of all the reactive species when the generation time is higher. Moreover, these radicals are enhanced with the gas flow. Meanwhile, these ones are decreased.